let's welcome Naci Saldi.
Okay.
Floor is yours.
Yeah. Thank you for the introduction and thank you for the invitation. It's a pleasure for me to give a talk at this online seminar. So first of all, can you hear me properly? Because my headset is not good enough.
Yeah, I can hear you.
Yes, we can hear you.
Okay, perfect. Good. So this talk is about stochastic teams. In particular, I will be considering existence of optimal policies in stochastic teams. And to do this, what I will do, I will actually introduce a topology for policies in stochastic teams. And using this topology, I will first establish that this set of policies are compact. And then I will also prove that the cost function under this topology is lower semi-continuous. And finally, using Weierstrass extreme value theorem, I will conclude the existence of optimal policy for stochastic team problems. Okay. So this is the outline of my talk. I will first introduce Witsenhausen's intrinsic model for team decision problems. And after this introduction, I will introduce my topology for optimal for team decision rules. Okay. This topology was indeed first introduced by Borkar to prove the existence of Markov policies for continuous time stochastic control problems under ergodic cost function. And then using this topology, I will establish the existence of optimal policies. And at the end of this talk, I will also apply my finding to the celebrated Witsenhausen's counterexample and prove that there exists an optimal policy for Witsenhausen's counterexample as well. So this is the Witsenhausen's intrinsic model for teams. Okay, sorry. So here we consider sequential team model, which means that agents are acting in a given order. And we have a state space X, and we have n agents, and each agent has its own observation space Yi and action space Ui. These spaces are Borel spaces, and we are also assuming that action spaces are locally compact. We have a probability measure P on the state space, which describes the uncertainty on the state variable little x. And each agent observes some random variable. For instance, agent I observes random variable Yi, which takes its value in capital Yi. And Yi, little Yi, is a noise corrupted version of the state X and the previous actions applied by previous agents. So for instance, Yi is a noise corrupted version of X and the actions U1 up to Ui minus 1. Okay? And therefore we have a channel from state and actions Ui minus 1 to the observation Yi, and this channel is called observation channel, and for agent I it is denoted by Wi. Okay, and in this model we have a fully decentralized setup. Therefore, when agents design their control policies, they can only use their own observation. Okay, so for instance, gamma I is the strategy of agent I, and it is only a function of Yi, which is the available observation for agent I. And Ui is the resulting action of agent I. And here gamma I is a Borel measurable function from observation space Yi to action space Ui. So here, as I said before, we are in fully decentralized setup. And our goal is to minimize the following expected cost function. So C is a function of state observations and actions. And since there's a randomness on the state variable as well as on observation variables, we need to take its expectation, and we want to minimize this expectation by choosing proper control policies. And gamma bar star is called an optimal team decision rule if it minimizes this cost function. Okay? And our goal in this talk is to prove the existence of such a policy. Okay, and we will do this by introducing topology on the set of policies. Okay? So in team decision theory, we have two important information structures. So information structures dictates what, who knows what. Okay, and the first information structure that we have in team decision theory is static information structure. So in static information structure, observations is only affected by state of the nature. Or in other words, the observation channel Wi is a function of the state variable little x. So it does not depend on the actions of other agents. So do you have a question? Yeah, I heard something, but yes. So this is the static information structure. So agents cannot affect the observations of other agents by changing their policies. And another information structure is the dynamic one. In this case, at least one agent's observation is affected by action of at least another agent. Okay. And of course, dynamic teams are more difficult to analyze and solve. Okay. But we have a very important result, which is called static reduction. So under some absolute continuity condition on observation channels, we can always transform any dynamic team into a static team by changing the cost function as well as the distribution of state and observations. Okay, and since we can always transform any dynamic problem into a static one under this absolute continuity condition, in this talk we will mainly consider static team problems. Okay. So these are the application areas of team decision theory. So we can apply findings in team decision theory to network communication systems, smart grid transportation networks, robot control, and economic networks. Okay. So these are the applications areas. So as I said before, we are in a decentralized setup. Therefore, observations are not collected in a centralized unit. And because of that, the problems in team decision theory are quite difficult compared to the classical problems in stochastic control. Because in stochastic control, we only have one agent and all the information available to the date to that agent is collected in a centralized unit. And because of this decentralized information structure, unfortunately, we cannot apply classical techniques like dynamic programming, linear programming, convex analytic methods to team decision problems. And since this is the case, team decision theory has many open problems, and even proving the existence of optimal policies is difficult for team decision problems. Okay. And the most famous open problem in team decision theory is Witsenhausen's counterexample, and it has the following simple model. So in Witsenhausen's counterexample, we have two agents. Okay. Agent one observes the random variable y1, which is a standard Gaussian random variable, and designs its strategy gamma 1. And agent 2 observes y2, which is a noise corrupted version of the action of agent 1. So here v is again a standard Gaussian random variable. Okay. And based on this observation, agent 2 should design its policy. And the cost function that we want to minimize is the following. So it is some positive constant L times the L2 distance between U1 and Y1 plus the L2 distance between U2 and U1. Okay. So for this problem, what we know the existence of optimal policy. Okay, so Witsenhausen proved this, and there are other existence proofs for Witsenhausen's counterexample as well. And we also know that the policy should be nonlinear. Okay, so this is indeed the different part from centralized and decentralized control theory. Okay, because in centralized control theory, if you have a linear system with quadratic cost function, and if the underlying noises are Gaussian, then you know that the optimal policy should be linear. However, in Witsenhausen's counterexample, we know that the optimal policy must be nonlinear. Okay. So this is what we know about Witsenhausen's counterexample, but we still don't know what the optimal policy is. And also we don't know what the optimal cost function is. And we don't even have a good lower bound, okay, for the optimal cost function. Because in the literature, there are a lot of numerical algorithms developed for Witsenhausen's counterexample. But since we do not have a good lower bound to the optimal cost function, we cannot actually quantify if they are good enough or not. Okay. And what is the difficulty or the difficulties in Witsenhausen's counterexample? So let me try to explain this. Actually, the difficulty is the following: in the cost function C, two additive terms are conflicting. Okay. So for instance, if you want to minimize the first additive term in the cost function, then the second additive term becomes large, or if you want to minimize the second term, the first term becomes very large. So let me explain this by applying certain policies to Witsenhausen. For instance, first of all, if you want to make the L2 distance between U1 and Y1 minimum, you can simply apply the identity function as gamma 1. So if you apply identity function as gamma 1, then U1 becomes Y1. And therefore, the first term in the cost function becomes 0. But in this case, U1, since U1 is the same with Y1, U1 becomes a Gaussian random variable, and you are adding some Gaussian random variable V on this. And then by using this noise corrupted version, you want to estimate U1, okay? And the estimation error is the distance between U2 and U1, okay? But we know that when you have a Gaussian random variable, and if you add a Gaussian random variable on that, then estimating this Gaussian random variable is quite difficult, and also the estimation error is quite large. Therefore, in this case, the L2 distance between U1 and U2 is very large. Okay? So, yes.
Naci, do you want us to interrupt now, or?
Yeah, you can interrupt anytime you like. It's fine for me.
Because you are talking about the closed form solutions for this, I don't know if you knew that we actually found the person by person optimal strategies for this.
Witsenhausen's counterexample?
Yeah, person by person, not the global.
Okay, I see.
It's two nonlinear equations. We did some simulations and they predict everything that Witsenhausen was saying, but also shows something which I think is important. I need to mention it. For certain parameters, linear strategies are optimal.
Okay.
I don't know if you know about this. So I just wanted to mention it to you.
No.
Yeah, is not for all parameters that nonlinear strategies are optimal.
Probably
for certain parameters that nonlinear.
When L is small enough, right? I think.
Not necessarily, but we had a recent paper at automatic ACC, and it has all this with simulations and all this. I think you will find it there. Since you are interested.
Can you send me the paper?
Yeah, of course. Yeah.
Okay, so if you send me the paper, so I want to read.
I just wanted to mention it now that you are on the topic.
Okay, yeah, perfect.
All right.
Okay, yeah. Right. Thank you. So, okay, thank you for the comments. Okay, so let me continue. So conversely, here what we can do, we can try to minimize the second term in the cost function. In that case, what we can do, we can apply the following simple policy as gamma 1. So let us pick some positive real number a. Okay, so let us pick this real number very big and apply the following policy as gamma 1. So if y1 is positive, okay, map y1 to a, and if y1 is negative, map y1 to minus a. Okay. So if you do that, then the distance between a and minus a is quite large. And therefore, if you add some Gaussian noise V on these, then agent 2 can easily estimate the value of U2, okay? Because it's either a or minus a. Although we have some noise on these two numbers, we can easily separate a and minus a if they are far away from each other, okay? And therefore, with this policy, we can make the second term u1 minus u2 minus u1 square very small. However, in this case, the first term in the cost function is quite large. Okay? So as you can see, these two additive terms in the cost function are conflicting, and because of this conflicting situation, finding the optimal policy for this analysis counterexample is quite difficult. Okay, so before I will introduce the topology, let me talk about the static reduction of dynamic teams. So here, if we have the following absolute continuity condition, we can always transform our dynamic team problem into a static one. So the condition is the following. We are assuming that WI, which is the observation channel, is absolutely continuous with respect to some reference measure QI for any state variable X and for any actions UI minus 1. Okay? So if you have these absolute continuity condition, then you can write the probability of S under the conditional probability of the set S under WI given state X and actions UI minus 1 in the following integral form, where Fi is the corresponding density function. Okay? In other words, for any X and UI minus 1, okay, the observation channel has a density with respect to some common reference probability measure. And if this is the case, then we can apply the following trick. So we can write the cost function of any joint policy in the following form. Try using my pen. So we can write my cost function of joint policy in the following form. Here, Fi's are density terms. And what we can do, we can actually incorporate these density terms in the cost function. So by doing this, we will get a new cost function, C tilde, okay, where C tilde is the product of the original cost function and the density functions. And then we can also define new probability measure over, okay, state and observations. And this team problem with cost function C tilde and distribution P tilde is equivalent to the team problem that we have at the beginning. And in the new team problem, as you can see, okay, the observations are in product form, okay, and they are independent with each other, and they are also independent with the state variable. Therefore, okay, therefore, this new team problem is indeed a static team, and it's equivalent to the original dynamic team problem. And this trick is very similar to the trick that is applied in nonlinear filtering theory, which is called Kirsanov measure transfer, right? So in nonlinear filtering theory, we have some observation process, which is actually a noise corrupted version of the state process. by changing the reference probability measure, you can actually make the observation process independent of the state process, right? Okay, we are actually doing the same here. Okay? By changing our reference probability measure, we can make our observations independent of the state and as well as independent of each other, okay? And obtain the static problem. And since we can do this transformation under this mild absolute continuity condition, I will always assume that in the remainder of this talk, I will consider only the static T problems. I will establish the existence for static T problems. And since we have this transformation, then we can apply our findings to dynamic team problems as well. Dynamic team problems as well. Okay. Good. Now it's time to introduce the topology. Okay. First of all, I need to enlarge the policy space for each agent. So at the beginning, I was assuming that policies are deterministic. So they are deterministic functions from observation space to action space. Now to put a topology, I need to also allow agents to apply randomized policies. Therefore, I'm assuming that policies are now functions from observation space to the set of probability measures on actions. Okay, so in other words, agents are allowed to use individual randomization. And here I'm endowing the set of probability measures with topology. Okay, so what I will do now, I will first prove the existence of optimal randomized policies, and then using the Laplace irrelevant information theorem, we will deduce that there exists a deterministic optimal policy as well. And I will define the topology on this set of randomized policies. And to be able to define a topology, I need to assume the following absolute continuity conditions. So since we are in a static case, observation channels only depend on the state variable x, and I'm assuming that this observation channel is absolutely continuous with respect to a reference probability measure mu I for any state variable x. Okay, so this is true for each agent I. Therefore, each agent I has an observation channel with a density, and the density is Qi. Okay, and this assumption is always true for static reduction of dynamic things. This is obvious. Okay, and now I need to introduce some notation and also give some definitions. So here, if E is a locally compact metric space, then C0E denotes the set of continuous real functions vanishing at infinity, and I endow this set with supremum norm. Mu E and PE denote the set of finite signed measures and probability measures on this set E. And if E1 and E2 are two sets, and if mu is a probability measure on, not probability measure, finite signed measure on the product of these two sets, then this notation here denotes the marginal of mu on E1. Okay. And in this talk, we have two important convergence notions for probability measures. The first one is weak convergence. Okay, so the definition of weak convergence is the following: the sequence mu n of probability measures converge to probability measure nu weakly if the integral of any bounded continuous function with respect to nu n converge to integral of the same function with respect to nu. Okay, so this is the definition of weak convergence for probability measures. And another convergence notion that is important for us is total variation convergence, and the definition of total variation norm is given as follows. So the total variation distance between mu and nu is defined as 2 times supremum of mu b minus mu b, where b runs over this over Borel sets. Okay, so this is the definition, and we can alternatively write the total variation distance using integrals as well. So in the integral form, we are taking again supremum of the integral of f with respect to nu minus integral of f with respect to nu, where f is a measurable function whose supremum norm is less than 1. Okay. And the second variational characterization of total variation norm is very useful, because using this variational characterization, we can obtain the following inequality. So here in this inequality, I'm assuming that function g is a bounded function. And on the left of this inequality, we have the difference between the integral of g with respect to mu and the integral of g with respect to nu. And I can upper bound this difference by the supremum norm of g times the total variation distance between mu and nu. And actually, we will use this inequality in the proof of existence result. Okay. Good. And now, before the definition of topology, I need to also introduce the following sets. So here, L infinity set is the set of functions from yi to set of finite signed measures on ui that are bounded. Okay, so these are bounded functions. So here we are actually taking essential supremum of this function, and the essential supremum operation is with respect to reference probability measure ui. Therefore, L infinity is the set of bounded functions from yi to set of finite signed measures on ui. And here L1 set or L1 space is the set of functions from yi to the C0 functions on ui. Okay. With finite L1 norm, of course. And the L1 norm is defined like that. Okay. And now we have the following duality relation between these two spaces. First of all, we know that C0, the topological dual of C0 ui is the set of finite signed measures on ui. Okay. So this is by Rie's representation theorem, and this is true when ui is locally compact. And using this topological dual result, we can also establish the topological duality result of the space L1 and L infinity. And it states the following: the topological dual of L1 space that I defined in the previous slide is the L infinity space in the same slide. Okay. And since we have this duality relation between L1 and L infinite spaces, we can actually put a weak star topology on L infinite space induced by L1 space. Okay. So this is indeed the topology that we will use, because what is L infinite space? It is this bounded functions from yi to set of finite signed measures. But remember, our randomized policies are functions from yi to the set of probability measures. Therefore, I can view my policy space for agent I as a subset of this L infinity space. And therefore, I can use the same topology for my policy space induced by this L1 space. This is indeed what I will do. So gamma I, which is the policy space or agent I, is the set of functions from yi to set of probability measures on ui. Therefore, gamma I is indeed the subset of the L infinity space that I introduced before. So I can also use the weak star topology induced by L1 space on gamma I as well. And this is indeed the topology that I will use to prove the existence. And what properties do we have for this topology? First of all, since PUI is a bounded subset of MUI, we can also conclude that gamma I is a bounded subset of this L infinity space. Therefore, by Banach-Aloğlu theorem, gamma I is relatively weak star compact. Okay. And since C0 UI is separable, okay, I can also conclude that gamma I is relatively sequentially weak star compact. And what is more, I can indeed introduce some metric on gamma I space, which is consistent with this topology. Okay. And this relative sequential weak star compactness is very important for the existence result. Okay. Therefore, we have these properties, which are very nice. Unfortunately, gamma I is not weak star closed under this topology. Okay, so this is a negative part of this topology, and let me show you an example where you don't have closeness. So in this example, yi, ui are reals, and I define two functions, gamma n and gamma. They are functions from yi to set of finite sign measures on ui, and gamma n is defined as follows. So it's a constant function, and for any yi, gamma n, the output of gamma n is the Dirac delta measure delta n. Okay. So for any yi, this is the output of gamma n. This is the Dirac delta measure at point n. What is the definition of this? It is the probability measure which is concentrated at a single point n. Okay. Good. So this is the definition of gamma n, and the definition of gamma is the following. It is also a constant function, and for any yi, the output of this function is the degenerate measure 0. Okay. So here this measure 0 is a sub-probability measure, and it gives zero measure for any subset of ui. Okay. And actually, I can prove that gamma I converges to gamma in weak star topology that I introduced. And since gamma is not a policy because the output of gamma is a sub-probability measure, then I can conclude that our policy space is not closed under this topology. And to prove the convergence of gamma n to gamma, you need to compute the following limit. So let us pick any g in L1 space. Then the integral that we have over here is the duality pair between g and gamma n. Okay. So where g is in L1 space, gamma n is in L infinity space. And if I can prove the convergence of this duality pair to 0, and since gamma is the 0 measure, the output of the gamma is always the 0 measure, I can conclude that gamma n converges to gamma in weak star topology. And I can prove this as follows. So first of all, since the gamma value of gamma ny is the Dirac delta measure at point n, the inner integral is indeed the value of the function gamma y. So remember, for any y, gamma y is a function of ui, and if you integrate this function with respect to the Dirac delta measure at point n, you will get the value of this function at point n. Okay. So therefore, this gamma y n is the value of the inner integral. And since everything is bounded, I can put the limit inside the outer integral. And now I can conclude that this limit is 0. Why this limit is 0? Because for any y, gy is a C0 function on ui. Therefore, it vanishes at infinity. So as n goes to infinity, since n also converges to infinity, gy n converges to 0. Okay. As a result, the value of this limit is 0. And if this is the case, then I can conclude that gamma n converges to gamma in weak star topology. And since gamma is not a policy, we can conclude that gamma I is not closed. Okay. So what I will do in the proof of the existence theorem, I will try to avoid this degenerate case. So by putting some conditions on the cost function and on the observation channel, I will try to avoid this situation so that our policies will not converge to some objects where the output of these objects are sub-probability measures. Okay. So this topology was first introduced by Borkar and Arapastasis to prove the existence of randomized Markov policies for continuous time stochastic control problems with average cost optimality criterion. And we will use the same topology here to prove the existence for team decision problems. And let me now continue with the existence proof. So before this proof, let me also explain to you another method that was used in classical stochastic control as well as in team decision theory to establish the existence of optimal policies. This method is called strategic measure approach. Okay. So let me explain what this approach is. So note that any strategic gamma bar induces a probability measure on state observations and decisions like that. Okay. Okay. So any gamma bar induces this probability measure on state observations and decisions. Okay. Where P is the joint distribution of state and observations, and gamma bar DUY is the conditional distribution of actions given observations. But this gamma bar, this conditional distribution, should have the following product form. Okay? So here, this indicates that UI only depends on YI. Okay? So this comes from the information structure of the problem. Okay? So remember, we are in a decentralized decentralized set. Therefore, UI can only depend on YI. Therefore, this gamma bar, this conditional distribution, should satisfy this product form. And in the literature, the joint distribution of state observations and decisions are called strategic measures. Okay. And what we can do to prove the existence of optimal policies using strategic measures, we can do the following. We can first define the set of all strategic measures. Okay. So this set is denoted by E. And since it's a set of probability measures, you can put a topology on this set. In general, people are using weak topology, so you can put a weak topology on this. And then if you can prove that this set is compact with respect to this topology, and also if you can prove that the cost function with respect to strategic measures is lower semi-continuous, then by Weierstrass extreme value theorem, you can conclude the existence of optimal policy. However, in strategic measure approach, proving the compactness of this set is quite difficult. And the problem is the following. So suppose you have some sequence in the set E, like Qn, and this sequence converges to some probability measure Q. And it is quite difficult to prove that this probability measure Q, which is the limiting measure, satisfies this conditional independence property. So in other words, it's difficult to prove that in the limit, you can preserve the information structure of the problem. Okay? So this is the main difficulty in strategic measure approach. And to prove that in the limit, you can preserve the information structure under strategic measure approach, you need to put quite restrictive assumptions on your observation channels. And even if you can do this, the proof is quite complicated. Okay. So in the following paper, actually, authors establish this. So here I'm stating the main theorem in this paper for compact action spaces, but they also proved existence result for non-compact action spaces. For compact action spaces, what are the assumptions? So again, we have density assumption on our observation channels. And these densities are continuous, and they also satisfy some restrictive uniform continuity condition. Okay, and under these conditions, you can prove that this strategic measure space is weakly compact. In particular, you can prove that you can preserve the information structure in the limit. And if your cost C is also lower semi-continuous, then using this compactness and lower semi-continuity, you can deduce the existence of optimal policy. Okay. What is the disadvantage of this approach? First of all, you need to put quite restrictive assumptions on the observation channel or on the density functions. And the second disadvantage is the proof. The proof is quite complicated. Okay. In this paper, the proof is quite complicated. So what we will do in this work, okay, to overcome these obstacles, instead of putting a topology on strategic measures, we will directly put a topology on policies. Okay? And by this way, in the limit, we can preserve the information structure. Okay? And using this topology, we can actually easily establish the existence of optimal policies. And therefore, the two advantages of our approach are the following. First, we can relax the conditions significantly, and also the proof of our existence result is quite simple. Okay? This is two advantages of our work. And before I will state the result, let me also introduce some notations, some assumptions. Okay, so to introduce these assumptions, I need to define the following objects. So for any L, gamma L is the set of policies whose cost function is L close to the optimal cost function, and let SL is the corresponding strategic measures. And for each I define SLI as the set of marginal distributions of observation and action of agent I when our strategic measure is in this set SL. Okay.
Sorry, Naci.
Yes.
Just a clarification. So isn't J star here is defined as the infimum, because we still have, like, the whole point is to prove existence, right? So I don't know.
Yeah, it's infimum. Yeah.
Okay. All right.
Yeah.
Thanks.
Okay. And here are the assumptions. So first two assumptions are quite weak. So cost function is lower semi-continuous, and observation channels are continuous with respect to total variation distance. So for instance, if density functions are continuous, then assumption B is correct. And we also assume that for some L, these sets SLIs are relatively compact with respect to the topology. Okay. This is the third assumption, and indeed the third assumption is the strongest assumption here. And it is true when action spaces are compact. Okay. And for non-compact action spaces, we need some growth condition on the cost function C. For instance, if your cost function is a quadratic function of actions, you will always have this growth condition, and you will always conclude that these sets are relatively compact with respect to the topology. Okay? And this is the main result of our work. Okay, under density assumption and under assumption E, there exists an optimal policy. And also, we can choose this optimal policy deterministic by using Blackwell's irrelevant information theorem. So how much do I have? Do I have 10 minutes? What minutes?
Yeah, you have 10 minutes. I mean, the time is actually flexible, so. Yeah.
Okay. So thank you. Good. So in the remainder of this talk, I will try to give a sketch of the proof. So first, what I will do, I will give a sketch of the proof of the continuity of the cost function J when our cost C is compact, supported, and continuous. Okay? So if C is compact, supported, and continuous, then the cost function J is continuous with respect to the topology that we introduced. Okay? And I will give this sketch when the number of agents is 2 to simplify the notation. So here n is 2. So, and also I will also simplify the cost function. So cost function C is a function of x, y1, y2, u1, u2. And since it's a compact supported by Stone-Weierstrass theorem, it's enough to consider the cost functions in the following form. So I can consider the cost functions in the product form. Okay. Therefore, I'm assuming that C is a product of R, F1, G1, F2, and G2. Okay. Good. And let K is the compact support of function R. Again, these functions are F1, G1, F2, and G2 are compactly supported. and let gamma bar n converge to gamma bar in weak star topology. And I want to prove that if this is the case, I want to prove that this difference, okay, will converge to 0 as n goes to infinity. So if I can do this, then the cost function is continuous with respect to this topology. And I will upper bound this term in the following way. So we have two terms in the upper bound. The first term is the difference of the costs of gamma 1 and gamma 2 and gamma 1 and gamma 2. And the second term is the difference of costs of gamma 1 and gamma 2 and gamma 1, gamma 2. Okay. Let me denote these terms as L1 and L2n. And what I will do, I will prove that L1n converges to 0 as n goes to infinity. And you can do a similar analysis for L2n. Therefore, from there, you can conclude that your cost function J is continuous with respect to this topology. Okay. So before I will obtain an upper bound to L1n, let me define the following object. So for any x, let me define bx1 as a function of y2 and u2 as follows. But note that this function is a function of y2 and u2. And if you fix y2, then it becomes a function of u2. And as a function of u2, it's a C0 function. Therefore, I can view this bx1 as an element of L1. Okay, so it maps y1, any y2, to a function, C0 function on u2. Okay, good. Is this clear? For any y2, bx1 is a function on u2, which is also C0. Therefore, I can view bx1 as an element of L1. And let me explicitly write down L1n. So it is the cost function of gamma 2n and gamma 1n minus the cost function of gamma 2 and gamma 1n. And the integral forms of these cost functions can be written in the following way. And I can upper bound this difference by the supremum norm of R F1 G1 times supremum of the following quantities, where supremum is over the compact set K. So here, this term is the pairing, duality pairing of bx1, which is an element of L1 space, and gamma 1n, which is an element of L infinity space. And similarly, this is a duality pairing of bx1 in L1 space and gamma 1 in L infinity space. Okay. And if I can prove that this term, supremum term, converges to 0 as n goes to infinity, then I'm done. And I will prove this by proving that the bx1s are totally bounded when x runs over this compact set K. And I will establish this using the variational characterization of total variation distance. So if you pick any x and x prime, then the L1 distance between bx and bx prime can be written in the following form. And I can upper bound this L1 distance using the variational characterization of total variation distance as follows. So it is upper bounded by the supremum norm of f times G1 times the total variation distance between the observation channel W1 evaluated at x and observation channel W1 evaluated at x prime. And we assume that W1 is continuous with respect to total variation distance. Therefore, from here, I can conclude that bx1s, where x runs over compact set K, this set is totally bounded in this space, in L1 space. Okay. And using this total bounded result, we can prove that the limit of the supremum term in the previous slide converges to 0. Okay. And this actually completes the proof because we can establish the same analysis for L2n. Okay. And it converges to 0 as well. So what do we have so far? If our cost C is a compact, supported, and continuous function, then our cost function J is continuous with respect to the big star topology that we introduced for policies, okay? And the remaining, the proof of the remaining part is quite actually easy. So here, what we do, we will take a minimizing sequence gamma n's in the set gamma L. In other words, the cost function of gamma n is 1 over n close to the optimal cost function. And since our policy space is relatively big star compact, we can always find a subsequence of these policies which converge to some gamma star. So this gamma star may not be a joint policy because our policy space under this topology is not closed. Okay, so this gamma star may not be a joint policy. Okay, but what we can prove the following. First of all, since C is a lower semi-continuous function, I can always approximate from below. I can approximate this function from below by compact support functions. And using this result, I can establish the following inequality. First of all, our J star is the optimal cost, and it is the limit of the cost functions of gamma n case, because this is a minimizing sequence. And I can write the cost of gamma nk as a supremum of cost of gamma nk when our cost is Cm instead of C. Okay? And since Cm is converging to C from below, this when I take its supremum, I will get the original cost function of gamma nk. And now if I change the places of supremum and limit minimum operations, then I will get a lower bound. But I know that if our cost is compactly supported, then our cost function J is continuous under this topology. Therefore, this limit converge to the cost function of gamma star when our cost is Cm. And if you take the supremum of this, if you take the supremum of this, you will get the original cost function of gamma star. Okay? So therefore, the original cost function of gamma star is less than the optimal cost. So if I can prove that gamma star is indeed a joint admissible policy, then I am done. Okay? And I can prove this by using the relative compactness of the set SLI. So remember what I want. I want the following for any I, gamma I star map any yi to a probability measure, not to a sub-probability measure. Okay, so this is actually the main problem in our approach. Okay? And I can prove this by using the relative compactness of SLI under weak topology, because gamma I and k cross mi gives the joint policy of action of action of agent I and the observation of agent I. Okay. And this sequence is a subset of SLI. And since SLI is relatively compact with respect to weak topology, this sequence must converge to a probability measure. So it cannot converge to a sub-probability measure with this relative compactness assumption. And since it converges to a probability measure, I can deduce that gamma I star, the output of gamma I star is always a probability measure. Therefore, gamma I star is a legitimate policy for agent I, and therefore gamma bar star is a legitimate joint policy for our team problem. And since the cost function of gamma bar star is less than the optimal cost, it's an optimal policy. Okay. Good. So this is the end of the sketch of the proof. Okay, let me quickly go over Wittgenhausen's counterexample. So this was the model in Wittgenhausen's counterexample, and I can always and it's a dynamic team problem because observation yi is affected by action ui. Okay, therefore, it's a dynamic problem, but we can always transform this problem into a static one. by using the simple trick. So if I define function f as follows, then I can write policy of any, the cost function of any policy in the following form. So here f is actually a density term of the conditional distribution of y2 given v1. PGs are the standard Gaussian distributions. And by incorporating f into cost function, I can equivalently write this cost in the following form, where my new cost function is C tilde and my new distribution is P tilde. And as you can see, P tilde is a product of two Gaussian distributions. And this form is equivalent to the original Witsenhausen's counterexample. And in this form, we have indeed a static King problem. And this is indeed the static reduction of Witsenhausen's counterexample. Okay. And if the static reduction satisfies the conditions that we have for the existence result, then I can conclude the existence of optimal policy for Witsenhausen's counterexample. And this is indeed the case. Okay. So remember, the cost function of Witsenhausen's counterexample is quadratically depends on the actions of agents. And because of this dependence, we can obtain the following groped conditions for this cost function. And using these groped conditions, I can actually prove that the sets SL1 and SL2 are relatively compact with respect to topology. Okay, this was the hardest assumption that we had for existence. And other assumptions are automatically true for Witsenhausen's counterexample. So by theorem 2, I can conclude that there exists an optimal policy for Witsenhausen's counterexample. Okay. So in conclusion, what I did today, I introduced a topology for policies in team decision problems. And using this topology, I proved the existence of optimal policy. And then I applied these findings to Witsenhausen's counterexample. My former PhD advisor, Serdar Yüksel, also has some existence result. It's a complementary result. And the conditions in that paper are weaker than the conditions here. And in this result, my PhD advisor used the W star topology on set of strategic measures. Okay. Good. So that's all for today. So if you have any questions, I'm very happy to answer them.
Thank you, Naci, for the very detailed and interesting talk.